Bismillahirrahmanirrahim. So today we're going to start gas laws. As some of you might already have done with your teacher in the school, but even if you have, it's okay. We will revise, and if you haven't, then okay. So gas laws. Okay. Now for we are going to gas laws is basically the study of relationship between these three factors. Okay, temperature, pressure, and volume, provided the mass of the gas is fixed. Okay, provided the mass of the gas is fixed. Okay, so we study the relationship between these two factors. Now, the behavior of gas is very easy to understand if you keep the kinetic particle theory in your mind. Okay, which is like imagining that the atoms or molecules are like balls. Okay, and as you are increasing the temperature is the measurement of the average kinetic energy, right? So what happens when you increase the temperature? What happens when you increase the temperature? If for example, okay, let me see. Okay, if for example we have a balloon, okay, and I'm making like 5 particles in it. Okay, and if I increase, and if I keep it under the sun, if I keep it under the sun when it's too hot outside, then you can imagine what will happen. This will expand. You can see that it will expand. Now why is it expanding? No air is entering, no more particles are entering, but still it is expanding. That is because the average kinetic energy of the particles is increasing, and as the average kinetic energy increases, they collide more forcefully, more violently against the balloon. And so in doing so, they are exerting a force against the walls of this balloon, and that will result in the balloon enlarging or increasing in size. So the mass of the gas is fixed, but we are increasing the temperature, and that is increasing the volume. Basically, volume is the space which is occupied by all these particles while they are spaced out. Okay, while they are spaced out, meaning that volume also increases the space between the particles. Now, these particles can be atoms, can be molecules, depending upon the type of gas we're talking about, right? So that is easy to understand. That's common sense. We have already done that many times, maybe from grade 5. So you know that as the temperature increases, average kinetic energy increases, they go farther away from each other, and therefore they occupy more space, and that means increased volume, right? So increased temperature, increased volume. And so decreased temperature, what does decreased temperature do? Decreased temperature meaning that they lose their energy, their average kinetic energy, they are less active, and they come close together, the space between them decreases. So if you keep the same balloon in a refrigerator, or if you keep the same balloon on a piece of ice maybe, okay, then you will see that the same 5 molecules, no, 1 2 3 4 5 6, same 6 molecules will be closer together. Okay, my drawing is not that good. So the same 6 particles are in a small volume. The number of particles is the same, the size of the particles is the same, but you can see that they are occupying less space, and therefore the volume is less. That is because the temperature is less. So you can imagine this as, very active, rowdy children. Okay, I mean, imagine how much space they would need compared to sleepy, lazy children. You can easily lie them up on a bed, or in a small room. So because they are lazy, they are sluggish, they don't have that much kinetic energy, the space between them is less, and so we can squeeze them. Okay, so decreased temperature means decreased volume. Okay, this is easy to understand, right? But what is pressure? What is pressure? Pressure is force per unit area, right? Force per unit area is pressure. Now, what do we mean by pressure? Meaning that more force per unit area, meaning that we are squeezing them together. okay, squeezing them together. And so increased pressure would decrease the volume. Increased pressure would decrease the volume. Okay. Uh, so remember that when we are studying this, when we are studying the relationship of these factors, now you can see that both these are affecting the volume and in opposite manner. Remember, in science, whenever there are two factors affecting any property, we cannot study both the factors at the same time. We can study only one factor at a time. Because, why? Because if both the factors are simultaneously acting upon that property, we don't know what the change is about. I mean, for example, if the volume increased, we don't know the volume increased due to the temperature or the volume increased due to the pressure. We don't know. So we have to keep one factor constant. It is important while studying this relationship that we keep one factor constant and we study the relationship between the temperature and volume alone, for example, or between pressure and volume alone, keeping the other factor constant. Because otherwise, how would we know that this change is due to pressure or is it due to temperature? Therefore, it's important to keep one of the two factors constant. Okay, so we can study experimentally, practically speaking, we can study the effect of, we can have one cause and one effect. That's it. Okay, the other factor that is influencing should be kept constant. So one cause and one effect. Okay, like that. So we will keep the pressure constant and study the relationship between temperature and volume. Then we'll keep the temperature constant and study the relationship between pressure and volume. And then we'll keep the volume constant and study the relationship between pressure and temperature. Okay, so they have given these laws different names, after the scientists who worked on these laws. So Charles law, pressure law, and Boyle's law. You don't have to learn these names, but you should understand the relationship between the factors. Okay, you don't have to learn the names of these scientists or what you know but you should know what happens if the pressure is kept constant, or what happens when the volume is kept constant, and what happens when temperature is kept constant. And remember, these laws are applicable only when the mass of the gas is constant. Okay? Okay. Now, so, okay. So first, let's talk about the Charles law. Okay? In Charles law, we are keeping the pressure constant. In Charles law, we are keeping the pressure constant. So keeping the pressure constant, we will be studying the relationship between temperature and volume, and this I have already explained, right? As the temperature is increasing, the average kinetic energy of the molecules is increasing, they're going farther away, and so they're occupying more space and the volume is increasing, and vice versa. Okay, when the temperature decreases, the volume decreases. So that is easy to understand. And then this is one a picture that the book used in order to explain. If, for example, this is one volume V, okay, this is volume V, and we have a particular number of atoms or molecules here. And when we increase the volume, when we double the volume, okay, keeping the temperature constant, no, temperature is, oh sorry, we are increasing the temperature. Yeah, we are increasing the temperature, keeping the pressure constant. Now what is pressure? Pressure is force per unit area. Force per unit area, meaning that when the particles collide against the wall, they exert a pressure, they exert force, right? When the particles collide against the walls, they exert force. Now that force per unit area is the pressure exerted by the gas on the walls of these containers. Okay, so if the pressure is constant, meaning force per unit area, if you want to keep the force per unit area constant, meaning pressure constant, but you are increasing the temperature because you are providing heat. Now if you want this to be constant but you are providing heat, That means you are providing kinetic energy, and that means they must be colliding more violently, more forcefully. No, on my screen it's tilted. Okay, on my screen this is straight. Okay. So, if you want to keep this pressure constant, and you are increasing the kinetic energy, now normally what would happen is that if you're providing energy, the particles will strike the wall with greater force, more violently. So force per unit area should increase, but we are keeping the pressure constant. If you want to keep the pressure constant, you have to double the volume. Why? Because then that force will be distributed over twice the area. The force would be distributed over twice the area. Therefore, the pressure would be constant while the temperature would be raised. Okay? So if you want the pressure to be constant, you have to increase the volume. And you can also look at it this way, that the molecules will, are pushing the piston up and therefore increasing the volume, because they want the space between them to be increased. So the temperature is raised, the volume is raised, but the pressure is the same. Okay? Is there any question regarding this? You can raise your hand now and you can unmute yourself. So this was Charles' law. Okay, is there any question? So if the pressure has to stay constant, the frequency of collisions should stay constant. And that is constant only if the volume is doubled. If the volume is doubled, then the force is distributed over a greater area, and so the pressure is constant. So nobody is raising hand. I will assume that there is no question. Okay. Then we move on to Boyles law. And I hope you guys know what pressure is, and all those definitions of pressure for gas and everything. I'm not doing that because that's why I shared my previous pressure class in the group. If anybody has any confusions regarding the concept of pressure and gases and all that stuff, then they can refer to that recording, or they can read chapter 16 of the book. Okay, now here in Boyle's law, so I'm first explaining you the kinetic theory of particles. Okay, then we will move on to the formulae and the graphs. Okay, so here Boyle's law is when the temperature is kept constant. Now here I'm keeping the temperature constant, but what I'm doing is I have halved the volume. So volume has decreased. And so what about the pressure? What do you think would happen to the pressure? Yes, Zainab? And also explain why.
Miss, the pressure would increase as the volume is inversely proportional to the pressure. So if the pressure increases, the volume decreases.
No, explain me in terms of the kinetic theory. Explain me in terms of the kinetic theory of matter, of particles.
So if the volume decreases, then there will be less area for them, so they would strike against the surfaces more often. I guess that would make them move a bit faster.
So yeah, so because the mass of the gas is fixed, that means the number of particles is the same. So force is divided over a smaller area. Okay, pressure is force over area, right? So okay. So because the force is the same, but the area, if you are decreasing the volume, the area would decrease. What do I mean by area here? Area of the wall, okay, against which these particles are colliding. So because I have halved the volume, now see, initially they had this area. For example, I'm talking about one side. They had this area to collide against. Here they have half that area, okay, to collide again. So you can see that now the same force is the same, but the area is less. So this is decreased. So pressure would increase. Okay. So halvening the volume would double the pressure. What does that mean? That this means inverse proportionality. Inverse proportionality means that one quantity decreases by the same amount as the other quantity increases. Okay, so but you know, the only difference is that volume is decreasing and the pressure is increasing, but they are doing so by the same amount. If volume is halvening, pressure is doubling. Okay, that's called so we'll talk about the graphs and the formulae later. So understand the kinetic theory, because I feel that understanding kinetic theory of particle is easier, and then once you understand that, understanding the formula would be even easier. Okay, so that was Charles' law, Boyle's law, and then there is pressure law. The third one is called the pressure law, and in that the volume is kept constant. So that is easy. Volume is constant. So that means which two quantities are we trying to study? If the volume is constant, we are trying to study temperature and pressure. Now, temperature and pressure, they go up and down together. What does that mean? That as you increase the temperature, you're increasing the pressure. And when you're decreasing the temperature, you're decreasing the pressure. How? Easy to understand. That as you're increasing the temperature, you're increasing the kinetic energy and increasing the force with which the particles are colliding against the wall of the container, and therefore greater force per unit area exerted on the walls. And that force per unit area is pressure. So as temperature increases, the pressure increases as well. Okay? So now, once we have understood this particle theory, kinetic theory of particles. Okay, Nabil, do you have a question? Yes, beta?
Yes, I have.
Okay.
Yes, why we are keeping something constant in everything? Like we kept constant in Boyle's law, temperature constant, and pressure law, volume constant, and in the first one, Charles law, pressure constant. Why is that?
I have already answered that question. Who will answer that question? Who will answer Nabil's question? I just answered it. The one who will answer this question, I will understand that that person is paying attention. Is that person is with me? Yes, Zainab?
Miss, I think we would keep everything constant because, like, if we increase the temperature a lot, then particles would be moving a bit more faster than they would normally. And if if we like if we decrease the volume or something, then the pressure would also be increased. So we want to have a normal situation, I guess.
I guess.
We want to have a normal situation.
See, I answered this question in right now. I mean, a few moments ago, I answered this question. Okay, let me ask Amna. Yes, Amna?
Yes, because we have to keep one thing constant, so we can see like while one thing is constant, we have to see the others, the changes in the others.
Right. Yeah, yes, you are correct. You want to complete your sentence? See, if for example, so okay, temperature increases the volume and pressure decreases the volume. If for example, volume is increasing, for example, in some experiment, now Nabil, I'm trying to answer your question. If volume increases, now both the factors are affecting it, right? But so if both the factors are affecting it, how do we know that this volume is due to the increase in pressure or due to the decrease in increase in temperature or decrease in pressure? How do we know? We don't know, right? When we are scientifically carrying out experiments, if both the factors are allowed to change freely, okay, we don't know that is this volume due to the increase in temperature or is it due to the decrease in pressure? We don't know. Okay, so in order to keep our experiments reliable, okay, in order to understand the experimental results in a better way, we have to keep the other factor constant so that we can study the relationship between the other two factors, the rest of the two factors, properly. Okay, like why do you have control experiments? Why do you have control experiments? You keep all the other constants, all the other factors constant, except for the one that you are observing, right? So you can say that this is that factor that has to be kept constant. Nabil, did you understand? Please let me know.
Yes, Miss, I did.
You understood? Okay, good. Is there any other question before I move on? Please, you can unmute yourself. You first raise your hand and then unmute yourself. I'm amazed at the fact that, when the chat box was enabled, you guys would bombard me with questions, relevant and irrelevant. And now when I am asking you to ask questions, after unmuting yourself and after, identification, you don't. There are no questions. When there are no questions, there are two possibilities. When you get no questions, there are two possibilities. Either you're too genius, so you don't even need these classes, or you never paid attention. You never paid any attention. So it's either one of the two. Okay, Yusra. Yes, Yusra?
Miss, can you repeat the Charles law? I'm a bit confused in that.
What is your confusion?
Miss, the how did you link it with pressure? That pressure formula, fourth law area.
Okay. This. Okay.
Yes.
So, okay. So, did you join us late?
No.
Okay. Okay. So, yeah, this is simple, real simple, that, when I'm increasing the temperature, but I want the pressure to be constant. So if you want to keep the pressure constant, but still increase the temperature, the only way to do that is to double the volume, because you are distributing the force, because, as you are increasing the temperature, you are increasing the force because the particles are going to collide against the wall of the container with greater force. So if you want the whole thing to stay constant, you have to divide that force over a bigger area. Okay? So that's how the volume increases. But in fact, it does not only increase, but it increases by the same amount as the pressure, as the temperature decreases. Okay, and why does the temperature decrease here? So as the volume is increasing, the temperature is decreasing. Why? Because why do you think here the temperature would decrease? Yes, Zainab?
Miss, if the volume is increased, then the particles wouldn't hit the surface as much since there's a lot of area, so there would be less energy in them, and then the temperature would be decreased.
Okay, so okay, you are quite there, but you're not actually there. But see, you're saying that, as we have increased the volume, so what have we done? We have increased the space between them, and so they cannot collide with each other as much, and they will have to travel a longer distance because they have spread out over a greater distance, and so they'll have to travel a greater distance before they can collide with the other one. And so, in traveling such distance, they lose their kinetic energy. They lose that kinetic energy, right? So basically their overall average kinetic energy will decrease. So temperature will decrease. Okay. And so if you decrease the volume, the temperature would increase because they would collide more. And in colliding, they are increasing each other's kinetic energy. Okay. So average kinetic energy would increase here. Okay. Okay. Yes, Amina? Yes?
Yes, Miss, I have a question, but you didn't still talk about that.
Okay.
But while in school, our teacher told us that while Charles' law, she told about the formula that is V1 over T1 is equals to V2 over T2. How
Okay.
did we get that? I didn't understand.
Yeah, I'm coming to that. I'm coming to that.
Yeah.
Yes, I was first explaining you the kinetic theory of particles, and then we will deal with the formulae. Okay. So, okay, let me see. Okay, so if pressure has to stay constant, okay, this is only possible if volume increases. Okay, so this is done. This is done. Okay, Boyle's law is done. Pressure law is done. Charles' law is done. Now we will come to experiments. Okay, I will discuss the experiments first. Okay, excuse my drawing. Okay, I'm not good. Okay, so this is water. I didn't get time to color this. You know, maybe I should hire one of the artists. You know, we have a lot of artists. Okay, so this is water. Okay, we are trying to study Charles' law, which studies the relationship between temperature and volume. Temperature and volume. Pressure is constant. Okay, pressure is constant. Okay, so this is the water in a beaker. Okay, I have not colored the water. Okay, this is water. Okay, I hope you understand. This is water. So this is a capillary tube or just a tube. Okay, this is a capillary tube. The reason why we're using a capillary tube is because the bore is narrow, and so it's easier to have an airtight column. Airtight column meaning, you know, like we don't want any communication of this column. This is the air column understudy. This is the air column understudy. This is the capillary tube. Okay, and this is a drop or a few drops of sulfuric acid. Okay, this is sulfuric acid. Is it sulfuric acid, right? It's not anything else. Sorry. Yeah, this is sulfuric acid. Okay. Sorry about that. So this is sulfuric acid, and this is the column of air that we are studying. Okay, and this capillary tube is held against a ruler with the help of a rubber band. Okay, you can look at the picture on page 76. If you don't like my diagram, here, this one. Figure 18.2, page 76. Okay, page 76, figure 18.2. You can look at this diagram. Okay, so now we will be studying. So, and then we have a thermometer immersed within the water. Okay, and we are providing heat. We are providing heat at the bottom of the beaker, and the reason why we have stuck this capillary tube against a ruler is because we want to record the height of the air column. This is the air column which is under investigation. Okay, so I want to see how this height varies with temperature. Okay, so we can start with room temperature, or you can start with even lower temperature, but you know, if you want something lower, you will have to cool it somehow, maybe add ice cubes or something. So you can have your own values for temperature, but whatever value you choose, then you have to gradually increase the values. Okay, for example, let's say if we start from 10 degrees Celsius, okay, from 10 degrees Celsius you can increase to 15, and then 20, and then 25, and then 30, and then 35, and then 40, and so on and so forth. So you can increase the temperature of the water gradually. And so how will you do that? You know, you have to keep an eye on this, the reading of the thermometer. Okay, and you have to gradually increase the heating, okay, till you get the desired reading. Also, allow some time. When you have reached your desired temperature, you stop heating because you don't want the temperature to go any higher. Okay, and then you will stir this water a little so that the temperature of the whole mass of water is the same. Okay, because remember, this bottom part will be hotter than the top part because it is closer to the source of heat. If you want the whole mass of water to have the same temperature, for that you'll have to stir a little, okay, but stir gently. And you can stir with the thermometer, but I would prefer stir with some other stirrer because you don't want the mercury level to get disturbed by the movement. right? And then you will also wait for the mercury level in the thermometer to be steady. Steady means stable, okay? To stop at some level for, for some time so that you can record it, okay? Also, you have to wait for this air column to come to the same temperature as the water. Okay, so it will require some time. The process of conduction through the capillary tube and then into the air would take some time. So you have to allow for all these processes. So there are three things that you have to wait for. You have to wait for the whole mass of water to come to the same temperature. You have to wait for the mercury level to be steady. And you have to wait for the air column to come to the same temperature as the mass of water in the beaker, okay? So for that, these precautions are important, okay? Stop heating, we stir the water to ensure that the whole water is at the same temperature as the bulb, as well as the air column. So we want all these three things to be at the same temperature: the bulb, the water, and the air column, okay? Now, then why is it that we are only measuring the height? Why is it that the height is representative of the volume of the air column? Because the volume of the air column, or volume of any, okay, Ahmed, you wanna answer that question? Yes? Yes, Ahmed?
Yes, ma'am. I wanted to ask a question.
Okay.
Why is there sulfuric acid like in the air?
Why is it that sulfuric acid, what?
In the air, like it's not coming down.
Oh, you're saying why isn't it coming down?
Yeah.
That's a good question. That's a good question. Very good. Okay. See, these are few drops of sulfuric acid, and this is a capillary tube. The bore is very narrow. Okay, the bore is very narrow, and that's the reason why we are using capillary tube. So the weight of this is not enough. Okay, that means the pressure exerted by the air on this drop of sulfuric acid is greater than the weight. So the weight does not succeed in making it fall down. Okay, also remember, look at this. Okay, I don't have an orange marker right now. Okay, also look at this. What does this tell you? This tell you that the molecules of sulfuric acid are attached to the glass. Okay, they are attached to the glass, and the attraction between the sulfuric acid molecules and the glass molecules is greater than the attraction between the sulfuric acid molecules for each other. Okay, and that's why they're clinging on to the glass tube. This is called capillary action. I will not go into the details, but this force of attraction is greater than the weight. Remember, this is an enlarged diagram. I have enlarged it for your better understanding. But this is capillary, this is narrower than the straw that you use for sucking, juices and soft drinks. But this tube is narrower than that. Okay, this is a capillary tube. Capillary tubes are really thin, are really narrow. Okay, so the weight of the sulfuric acid is easily counteracted or easily opposed by, first of all, the pressure of the air which is beneath it, as well as the attraction between the sulfuric acid molecules and the glass tube. Okay, so I hope I answered your question, and that reminded me of another factor that I forgot to mention. What is the pressure? I said that the pressure is kept constant, right? Okay, so we understand that the pressure is constant, but what is it? What is the pressure? Yes, anybody wants to answer? Anybody wants to attempt to answer? It's okay. Yes, what is the pressure? It is constant, but what is it? Yes, Nabil?
It is
Yes?
the same pressure as it is in the air.
No, what is the pressure acting on this column of air? Okay, Ahmed? Ahmed?
It is the repelling force between the particles, I guess.
Sorry?
The repelling force between the particles.
Pressure. Okay. Okay, Amna.
Yes, miss. Pressure is the push on the sulfuric acid from both sides, like from below, from the air bubble, and even from the top.
So what is the pressure acting on the air column? It is?
Downwards.
No. Say it again. Can you please say your answer again? So the pressure on acting on the air column is?
No, I said the pressure acting on the sulfuric acid is upwards from the air bubble, and it is not letting it come down.
Okay, okay. Let me ask Saad. Yes, Saad? Yes.
The pressure is the, what do we call, the weight of the concentrated sulfuric acid downwards.
Yes. And that's it?
And the pressure acts on the side of the side of the glass, what do we call it, the side of the capillary tube.
And which is what?
Which is, I don't know, sir, miss.
Okay, okay. That's okay. Uh, see, the pressure acting on this column of air is atmospheric pressure. Okay, atmospheric, right? First is atmospheric pressure. We have atmosphere because this capillary tube is open, right? It's open to the outside. So atmosphere is in contact. It is open to the atmosphere. So atmospheric pressure will act upon it, plus the pressure due to this height of the sulfuric acid. Is that what you said, Sandus? You just said atmosphere. Yes, okay. So the pressure acting on it was atmosphere, okay, which is in connection with this capillary tube, as well as the pressure due to this, whatever this height is of the sulfuric acid. That will be the total pressure acting upon this column of air. Now, if you ask me that, you know, why isn't the atmospheric pressure acting on the sides of the tube? For that, you have to watch, you know, my previous class on pressure, the one that I forwarded in the group. Okay, that is the reason why we want this to be airtight. We don't want, you know, only atmosphere and this column of sulfuric acid will be acting on this column of air. So that is the pressure which is constant. Okay. Now, so my other question was, why is it that the volume of air column, like, you know, we don't calculate the volume of the whole thing. We don't calculate the volume. We're just looking at the height. That's it. You know, whatever this height is. Okay, 0, 10, 20, 30, 40. So my question is that why is it that we are only measuring the height? Why is it that we are only measuring the height? Why aren't we calculating the whole volume? Yes, because you know the volume of any 3D object, is what? You have done it in mathematics. Base area and multiplied by height, right? Base area multiplied by height. Now, whatever the height would be, the base area is the same, right? The base area would be the same because this is a uniform tube, so base area would be the same. So if the base area is the same, that means base area would stay the same no matter what the height is or what the temperature is. Base area would stay the same. It would only be the height that will change. So we can say that the volume of the air column is directly proportional to the height. And the height can be in any units, whatever the units of this ruler are, okay? Most probably centimeters, right? So we can confidently say that the volume of the air column is directly proportional to the height of the air column in centimeters. Okay. Okay. So as we are increasing the temperature, we are recording the height of the air column. Okay. And we will tabulate our results. We will make a table. Okay. We can make a table like this. Why don't I have a good marker? Okay. For example, so you can have your temperature in this column in degrees Celsius, and then height in centimeters in this column, and then you can go ahead and record your results, make a table like that, and then you can also plot the results in the form of a graph, okay, where your x-axis can be the temperature and y-axis can be the volume of air column. Okay, you can even do it the other way around. You can make temperature the y-axis and the volume the x-axis, but the shape of the graph will stay the same. Shape of the graph will stay the same, okay? Okay, what can I say about this graph? So what is this telling me about the relationship between volume and temperature? What is this telling me? Yes, Nabil? Yes, Nabil? You can unmute yourself. Okay, Amna. Yes, do you have a question?
No, I wanted to answer this.
You wanted to answer this? Okay, go ahead. Tell me.
Yeah,
What is the relation? Yes?
they'll keep constant.
Sorry, can you please speak loudly?
They'll be kept constant.
They,
Volume is directly proportional to temperature.
yes, that is right. Volume is directly proportional to temperature, but I'm talking about this graph. So what can you tell me about this graph? Whatever you can tell me by looking at it. So this is a straight line graph. So what do we call such graphs in math, in a mathematical language? What is such a graph called? It's
Constant.
called constant?
Linear graph. Linear.
Very good, Nabil. Linear. Who said that? Was that Nabil? Okay, good job, Nabil. Yes, this is called linear. Okay, can I call this directly? Can I call this? I mean, just by looking at this particular graph, can I say that volume is directly proportional to temperature? Can I say that?
Yes. Yes.
Yes.
Think again. Can I say that? Just by looking at the graph, can I say that the volume is directly proportional to temperature? But it's not passing through the origin. For direct proportionality, I think for direct proportionality, the graph has to pass through the origin. So yes, the relationship is linear, which means straight line. What does linear mean? That equal increase. Linear means that increases in y-axis is equal to the increases in x-axis, meaning that the increases in both y and x-axis are equal. So if y-axis is, for example, increasing by 2, the x-axis would also increase by 2. Or if y-axis is increasing by 3, the x-axis would also increase by 3. So whatever one quantity is increasing by, the other quantity will also increase by the same amount. That is when we get a linear relationship, linear meaning straight line. But since it is not passing through the origin, I will not call this direct proportionality. So volume of air column is proportional, but I won't call it directly proportional, but yes, they have linear relationship. Now, same relation, and can you also appreciate the fact that my points are not exactly on the line? What does that tell you about? What does that tell you? What does that tell you? My points are not exactly on the line. They're, like slightly here and there. So that means I estimated this line. I took the best fit. I took the best fit of all these points and I drew a line. Yes, Amna, tell me, what does that mean? Why aren't the points exactly on the line? Yes?
Yes.
They might be around, but we made a straight line because of our estimate.
Yes, yes. So what does that tell us? That, yes, Zainab?
Yes, Zainab.
Miss, maybe we can't keep an exactly same temperature. Or
Yeah,
like the temperature changes a lot also. So I don't think it's possible to keep a temperature exactly same all the time or something.
Yeah, oh yeah, yes, exactly. So practically speaking, we cannot have ideal values. So our values would be, a little deviated from the actual thing. Okay, and it's okay. This error is allowed. Okay, because we cannot have 100%. So we will take the best fit. Okay, so this shows practical errors. Okay, so the actual, so you don't have that perfect thing, as you see in the books. Okay, practically speaking, this is how you get. Okay, so you plot them, I mean, you jot the points down, and then you take the best fit. Okay, in ATPs and alternative to practicals, you will realize this. Okay, now if you plot pressure against time, you will get the same sort of graph, same thing, linear relationship, but not passing through the origin. Now, why is the graph not passing through the origin? Why is the graph not passing through the origin? Think, if the temperature is 0, the reason why it's not passing through the origin is because if the temperature is 0, what? Yes, Zainab. Zainab, I like the fact that you attempt to answer questions. I like it. Yes, Zainab?
Miss, I don't think normal room temperature is like about 24 degrees, and if to start from 0, we have to put the room's temperature very low then. Like the temperature of the surrounding may also affect.
See, if, for example, the graph was from here, for example, okay, just imagine. That means this point is telling me that at temperature 0 degrees Celsius, the volume is 0. And volume is 0, then, then where did the gas go? That means no particles at all. So practically speaking, it's not possible. You cannot have volume 0. You cannot have it. Okay, temperature is 0, and at temperature 0, you don't have volume 0. Okay, volume 0 means nothing, gone. Where did it go? Into the thin air? Where did it go? So that's practically speaking, that's not possible. Same is the case here. Pressure 0, there is always some pressure. You cannot have pressure 0. Okay, so practically speaking, we get a graph like this. Okay, now, yes, Nabil, I will take your questions in a minute. But then I want to show you this graph. So now we have, both the volume and pressure graphs were something like this against the temperature. They were straight lines, but they were not passing through the origin. And so, we extrapolated the graph. What does extrapolated mean? Extrapolated. This is an extrapolated graph, meaning that assuming that the behavior of the gas stays the same, we continue the graph. We continue the graph and see where does it touch the x-axis. Where does it touch the x-axis? And it is touching at minus 273 degrees Celsius. Okay, minus meaning that you go 273 divisions backwards, or you go 273 divisions on the left side, on the negative side. Yes. Now, scientists have given this point a name called absolute zero. Okay, absolute zero, or 0 Kelvin. Now, Kelvin is a different scale of temperature, but remember, appreciate the fact that there are 273 divisions, right, on the left, on the negative side. And so that is 0 Kelvin, right? And so that means if we go forward, if we move the same number of divisions forward, this would be 273 Kelvin, positive, right? This is positive. Because we moved the same number of divisions, but in a reverse direction. So this is in the positive direction. So this is 273 Kelvin. Okay, so that means one division of one division in the centigrade or the Celsius scale is equal to one division on the Kelvin scale. Is that what it means? Because this is moving 273 backwards and this is moving 273 forward. That means one division of 1 degree Celsius is equal to 1 Kelvin. Okay. Okay. Yes, Nabil? Okay, another thing before I Nabil, before I take question from you. Now since it is touching the origin, okay? If we take temperature at the Kelvin, now the graph is touching the origin. Now we can say that pressure and volume of a gas are directly proportional to the temperature in Kelvin. Okay, now we can say that. Now, because now the graph is passing through the origin. Now we can say that the volume or pressure of a gas is directly proportional to temperature, but in Kelvin. Okay, and remember all these calculations related to gas laws, temperature has to be in Kelvin all the time, no matter what, in all the calculations. If the question gives you temperature in degree Celsius, always convert it to Kelvin first. Okay, the units of pressure and volume can be used. I mean, you can use any units for as long as the units on both sides of the equations are the same, because they get cancelled out, but temperature has to be in Kelvin. Okay, now what is absolute zero? Let's talk about absolute zero a little bit. Now the reason why I drew this in a dotted way. Okay, first let me take Nabil's question. Yes, Nabil?
Yes, according to this, 1 Kelvin equals 1 centigrade. So, like for example, 10 Kelvin equals 10 Kelvins equal 10 centigrade, right? Is this the
I'm
conversion
saying,
scale?
no, see, what I'm trying to say is that one division of Kelvin is just as big as one division on Celsius. That's what I mean. Do you understand? See,
Yes,
this is,
okay.
yeah, what I mean to say is that this one division on 1 degree Celsius is exactly same as is exactly equal as one division in Kelvin scale. This is what I mean. Because you see, in different scales, sometimes, the smallest unit is of different sizes. Like, I don't think 1 degree Celsius is equal to 1 degree Fahrenheit. I don't think so. 1 degree Celsius is not equal to 1 Fahrenheit. I'm not sure, but I don't think so. But here they are. That's what I mean. Okay. Okay. Is that,
Okay,
was that the only question, or do you have any other? Okay. Okay. So now let's talk about absolute zero a little bit. Now, the reason why I made this graph dotted, why didn't I make it continuous? Why did I make dotted? Dotted means that we have not been able to, like, these values are not obtained by any experiments. Like here, we got these values from experiments. This graph is theoretically, meaning on a piece of paper, by practically we got values here. Practically we got values here, something like that. But then we extended it theoretically. We did not get these values from any experiments. Because why? Because this is not possible. This is not possible. Obtaining these temperatures and performing experiments at these extreme temperatures is not practically possible. Okay, therefore we just extended. Yes, Amina? Okay, I'm trying to unmute you.
Miss, I have a question.
Yes?
I have a question.
Yes? Yes,
Miss,
I'm listening.
this is the graph if we make pressure when it is directly proportional to volume, right? Like one side will be pressure and the other side will be 1/volume, right?
No. This is, I'm not talking about volume right now. I mean, no. That's different. No, the x-axis is temperature. You're confusing this with Boyle's law, I think. That I will come to that graph. This is not that graph. Okay, this is when this is between volume and temperature. okay, and or pressure and temperature, okay, keeping the other factor constant. Okay, no, this is not between pressure and volume. That graph that you're talking about, that is between pressure and volume. I have not come to that yet. Okay, okay, so let's talk about absolute zero a little bit. Okay, now absolute zero is theoretical, meaning practically it is not possible to achieve this. Okay, this is theoretical only, and we assume, or we think, the scientists think, that it is that temperature where the atoms or the molecules are absolutely static, meaning they don't move at all, they don't even vibrate, they have minimal vibration or no vibration at all, they have no internal energy. Internal energy is the sum of potential and kinetic energy. So at this temperature, the particles have no internal energy. Okay. So practically speaking, it is not possible to achieve this temperature, but yes, theoretically we do. Okay. And in your book, they have mentioned that substances behave very weirdly at around this temperature, absolute temperature, so much so that helium becomes a superfluid. Superfluid meaning that it has zero viscosity. I mean, you don't have to go into the details, but they behave weird. Okay, and I searched a little bit into it. I mean, it's not included, but it was very interesting that at absolute zero, atoms or molecules do not behave as particles anymore. Like in all these examples that I've been giving you, while explaining, I've always asked you to think of atoms or molecules as balls. I've even used balls myself to explain you stuff. But at this temperature, at absolute zero, the atoms or molecules, they don't behave as particles anymore, but they behave as waves. They behave as waves. And therefore, that's the boundary of that's the limit to our knowledge. Okay, so you can, I mean, the scientists have studied their behavior as well. That is a part of quantum physics, and we're not going to go into that, but it is very interesting. And just so that some substances conduct indefinitely in around absolute temperature, absolute zero temperature, meaning that if they start conducting, they'll keep conducting a current without battery. They will never go out of current. And some other substances, they become absolute insulators, they won't conduct at all. So that's weird, and we don't understand that. Okay. So whenever you want to convert degree Celsius to Kelvin, just add 273 to degree Celsius temperature. That's the way to convert degree Celsius temperature to Kelvin. You just add 273 to degree Celsius and you will get the temperature in Kelvin. Okay. Now Kelvin temperature is given a symbol of capital T, and usually in your book. And then degree Celsius is given, symbol is represented by a symbol which is a Greek letter called theta. Okay, so you just add 273 to degree Celsius and you will get a temperature in absolute, in the Kelvin scale. You will get the temperature in Kelvin scale. Okay. Okay, if you have understood that, so then let's move on. So this was Charles' law. Okay, this was Charles' law that we just discussed. Now let's move on to what was this? This is pressure law. This is pressure law, and in pressure law, what is constant? The volume is constant, right? In pressure law, the volume is constant here. Can you please turn the fan on and the AC on? Okay, the volume is constant. Okay, now again, I did not color this. This is all blue. This is water. Okay. Okay, another thing that I forgot to mention here in this Charles' law experiment is that make sure that this whole column is immersed in the water. Okay, like your air column should not be sticking out of the water. Your air column should not be sticking out of the water. The whole thing should be inside the water. Why is that important? Why is that important? Why should the whole air column be inside the water? Yes, Yusra?
Miss, I have a question for
Okay.
absolute zero.
Yes,
Miss, you
okay.
said that for absolute zero, the scientists say that they don't have any energy. Then how do they conduct?
That's what I said. We cannot conduct.
But you said that in the book it's written that some metals and compounds become superconductors.
Yeah, so they use a special apparatus and special when not in an ordinary laboratory, but they have now invented these special apparatus and special instruments with the help of which they do that, and only in very specialized circumstances. Okay, I hope I answered your question. Yes, Nabil?
Miss, is it necessary to use rubber band like it's mentioned in figure 18.2?
Yeah,
That
anyway, you can keep the capillary tube fixed to the ruler, and your readings should be accurate. So you can use anything, but provided it is not affecting your results.
okay, thank you.
Yeah. Okay. And but the idea is that the capillary tube is held against the ruler in such a way that your readings are precise and accurate, and no parallax error and no other errors. Okay. Yes, Ahmad?
Yes, teacher. Teacher, you said in the absolute zero, the energy vanishes, right? The potential and kinetic energy.
Yes.
So where does the potential energy go?
See, listen, I don't know where the energy goes, but the thing is that that's the temperature at which they don't have any energy. Okay, we are not going to go into the details. Okay, we're not going to try to understand their behavior, because as I told you that they stop behaving as particles, they start behaving as waves. So that's the end of the story for us. Okay. Okay. Yes, Zainab. Okay. Yes, Amina.
Miss, I want to answer him that he asked where does the energy go. So the
Okay.
energy goes, like energy is all given out to the surroundings because it is endothermic.
Yeah, the energy is lost. Of course, the energy is taken out. Okay, so that's how we decrease the temperature. Okay, so let's talk about this pressure law in which the volume is constant. So I asked you a question that why is the air column within the water? Why is the air column inside the water? Why is it important? And even in this, so let me explain this apparatus first. This is a round bottom flask. Okay, it is filled with air, and this diagram is the same as on page 77. Page 77. Okay, and we're doing this pressure law. Okay, I have a dirty book. Page 77. Okay, so this is a round bottom flask, again a beaker filled with water. Okay, and this is a thermometer to measure the temperature, and I think okay, they're not heating. Okay, so but the volume is constant. As you can see that the volume is not increasing, whatever, I mean, this is the whole volume, this is the volume, whatever the volume of the round bottom flask is. Okay, this is a Borden pressure gauge. Okay, we discussed Borden pressure gauge in that pressure class. Okay, in the pressure class, chapter 16. Okay, so I won't go into the details of how this works because we discussed it there. It has a pointer, and this pointer, it gives us a reading for the pressure. Okay, and so again we will make a table with two columns of values. One would be of temperature, because we are trying to study the relationship of temperature against pressure this time, against pressure. And the pressure unit can be pascals, can be atmosphere, whatever. I mean, it depends upon the instrument you're using. And the volume in this case is constant. Okay, so again, you can vary the temperature by providing it, with a heating source, by heating it up. And I think they should have mentioned heating here. Yeah, they should have shown heat, because otherwise how would you change the temperature? How would you change the temperature? There has to be some heating. So you can start from 10 degrees Celsius, for example, and then increase by 5 degrees Celsius gradually, 15, and then 20, and then 25, and then 30, and then 35, and then 40, and then so on and so forth. And then you can plot a graph of temperature against pressure, and the graph would be the same. Okay, pressure against temperature, the one that I just discussed with you. Okay, linear relationship. If the x-axis is in degrees Celsius, then the relationship is linear. Okay, not directly proportional, but if the temperature is in Kelvin, then yes, it is directly proportional. Now, I have a few questions regarding this. So this experiment is real simple. So as the temperature is increasing, the value here, the pressure will increase because the molecules will bombard against the walls of the container more violently. And so that would increase the pressure that can be measured with the help of this Borden pressure gauge. Okay, and so we can have this table. So my question is, why is it important for this round bottom flask to be immersed in the water? Yeah, I know I am out of time, so I will just finish this pressure law, and then I will finish this class. Okay, so why is it important for this round bottom flask to be in the water completely? Yes. Yes.
Because what we call it, so it avoids contact with the bottom of the flask. The water keeps it afloat.
Okay, if it contacts the bottom of the flask, then what happens?
Well, it will get directly heated without the water, and the thermometer would not be able to accurately measure the temperature of the round bottom flask.
Very good, Saad. That's wonderful. Very good. Well explained. Another reason, okay, why shouldn't it be sticking out?
So then it shouldn't lose the heat to the air.
Yes, because we are measuring the temperature of the water, and we are assuming that the temperature of the water is representing the temperature of the air. Okay, so if this air is above the water, it would come into equilibrium with the atmospheric temperature rather than the water temperature, which might be lower. Okay, or yeah, again, you mentioned it correctly, that if it is touching the bottom, it will be in direct contact with the heat, and so it will be higher than the temperature of the water. Right now, another thing that your book mentions is that this rubber tubing should be as short as possible. Why? This rubber tubing, which is connecting the round bottom flask with the Borden pressure gauge, this should be as short as is possible. Why is that? Yes, Ariba?
So that there are less errors when we are measuring the volume of air, because the
Volume
rubber.
of air? Are we measuring the volume here?
Oh, sorry, pressure.
Okay. Okay, so
And
yes.
and the rubber tubing, it will also contain some amount of air along, as well as the air which we have in the flask.
Okay.
So if it is longer, then there will be more air, so it will change the readings.
Yeah, basically, you see, the longer the tube is, the more distance it will have to travel. And so in the process, it will lose energy and it will cool down. And we are studying the relationship between temperature and pressure. So that pressure might be due to the cooler temperature. Okay, we don't want that. So the rubber tubing should be as small as is possible, so that the temperature here is the true temperature, is the temperature that we are studying. Okay, because we don't want the air to lose energy. Okay, so that's that. And then again, in this experiment as well, we will stop heating and we will stir a little so that the whole water has the same temperature. We will wait for the mercury level to be steady, and we will also wait for the air to come into the same with the same temperature as the water. Okay, I will not continue because it is Isha Salah time. So I will continue with the Boyles law in our next physics class. Okay. Okay, assalamu alaikum wa rahmatullahi wa barakatuh. Okay, wait, I can see Ariba's hand raised. Is there any question? If you have a question, then please ask me. Yes? Okay. If there's any question, you can ask me right now. Okay, assalamu alaikum wa rahmatullahi wa barakatuh.